computer. Let's get that. Okay, I went, like I said, I had to look at your assignments. You guys basically are getting the concept. I mean, some of the values were, wrong, but so I'm going to go through this slow enough, and at any time, please, like stop and ask where you might, if you don't see where the mistake is, it could have been just a mistake in your calculator. But if you don't see it, now's the time to ask me. So this way we can clarify any glitches that we might have regarding the, okay, so please don't be shy. Okay, so this was the assignment, and basically, okay, so here was a problem, right? You got a composite column, which is made of 2 steel plates, okay, and a wooden core. Transform the section into a steel and calculate the properties with respect to IX, SX, RX, IY, SY, RY, okay? Excuse me. Now, this is the modulusicity for the wood, which is a reasonable value. And of course, this is always going to be the assumed modulusicity for structural steel. And of course, since we are transforming the section into wood, therefore the wood is going to be the denominator and the steel is going to be the denominator to calculate the ratio. So in other words, N is E wood over E steel. And therefore I end up with a value of 0.457. Now I brought it here to 4 decimal places, but 0.48 would be accurate enough. If you wanted to put it to 0.5, that would be okay by me in a sense. So don't, Now the equivalent would, okay, and remember, whenever you're transforming a section, you always multiply the dimension that is parallel to the axes that you're transforming. Okay, so in other words, this is the dimension that is parallel to the axes, and therefore, I'm sorry, for the wood, yeah, for the wood, and so you measure always the one that is parallel to the axes, and therefore the wood will shrink down to a width of 6.65 millimeters. So if you want to write the answers down, and then you can go back and see if it was just a question of making a mistake on your calculations, and the ones that you did, I got it right. Thank you for doing so. So so right away, so this is what I end up getting, okay? So we get this very compressed section, okay? And of course, here what happens is that, what happens that the centroids here of this transformed section happens to coincide. Therefore, you don't have to use the parallel axis theorem to be able to calculate the section properties. And so therefore you can simply take this as being your B, take this as being your H or your D, whatever you guys want to use, okay? So the cross section is symmetric with respect to both axes, therefore the neutral axis coincides with the centroid. That's the first thing you should realize. So whenever you're doing sectional properties, look for symmetry. If you can find symmetry, you found the neutral axis, and therefore you'll save yourself the trouble of finding the centroid. That's number one. And then number two, here I have IX, in other words, the moment of inertia with respect to this axis here, that's why I call it IX, is IC plus AD squared, okay? Now, here, there's no D, so therefore this part goes to 0, and therefore I end up getting my IX value, okay? So I don't have to transform this section and move the individual regions into the centroid of the overall sections because everything coincides. The D goes to 0, therefore the IX value is there. Now, once I have my IX value, of course, the section modulus is the distance from the centroid to the outermost fiber of your section, okay? And that's the value of C. And of course here, the C value is exactly the same. So the SX here and the SX here would be exactly the same. So the stresses here would be the same as the stresses there. And therefore you only have to calculate one section modulus. And of course, now, like I said, when you do these things, if you're doing a metric, I do expect to see this in scientific notation, and I do expect to see this in scientific notation, because any steel handbook that you're going to open up, they all have the values written like this. So you might as well. And if ever you want to compare your value with what's in the book, you have to have it in the same format. So there's your section modulus. And of course, the Rx is simply, so the Rx is, of course, let me clear the drawing. Okay, the Rx radius of gyration with respect to x. Okay, so this was the definition of radius of gyration, if you remember. Okay, and we get Rx, and this is the formula that we use to calculate Rx. In other words, the moment of inertia with respect to the axis you want to calculate the radius of gyration divided by the total cross-sectional area. And therefore I get 176.6 times 10 to the 6. This should have been, this is 10 to the 6 divided by 5,330. And I get an Rx value of 57.8 millimeters. And of course it has to be millimeters because this cancels this to a square. And of course the square of this ends up being just millimeters. So the units are correct. Okay, so I hope you guys are correcting your assignments, and the ones that you got it right, that's great. Now, I want to do it with respect to the y-axis because I need to find out if this is going to be a column. I need to find out which is the weaker of the two. Okay, so here with respect to the y-axis, which means that I need to transform the dimension that is parallel to the y-axis. So I need to transform that section there. So the 200 multiplied by the modulus ratio number, the n, becomes 9.7 millimeters. So this whole thing shrinks down. So it ends up looking like a wide flange section. Okay. And so now here IY is equal to IC plus AD squared. Okay. Now this section here, you don't have to worry about the parallel axis theorem because the centroids coincide, but these two have to be brought to here. So therefore you're going to have to worry about, okay, so here you get, so here I just multiplied this by 2. In other words, this one and this one, that's 2 and 1/12. Now, whenever you're doing this, the base is always a dimension that is parallel to the axes. Okay, so here the base is 200. And the height is, of course, the one that is perpendicular to the axis, and the height is 10. Okay, so this is something that, how do you remember which is the base, which is the height? Base is always parallel to the axis, height is always perpendicular to the axis about which you're calculating the section properties. And of course, this is this part here. And the AD squared is, of course, 200 times 10 times the distance. In other words, the distance from the centroid of this and the centroid of that to the centroid of your overall section, of your transform section, and that of course should be 75. Okay, I have it here, and that's 75 squared. And this one here only has 1/12 the base times the height because the area, the distance from the centroid of this section to the centroid of the overall section is 0. Therefore, I don't have an AD squared. And and I end up getting an IY equal to 24.7 times 10 to the 6. Now the same thing, the section modulus is the distance from the outermost fiber to the centroid. And in this case, this would be, of course, I think it's 80 if I'm not mistaken. So yeah, so it's 24.7 times 10 to the 6 divided by 80. And I hope you appreciate that if you make a mistake here, you'll make a mistake here, you'll make a mistake there. So this, of course, is going to be very important that you calculate it correctly because any mistakes there just carry through to the rest of your values. Keep that in mind. And of course, now, as far as the same thing, same equation, the only difference is that you always use the same area. The only difference is that, I'm sorry, the area, but it's IY divided by A. And here we end up getting an RY value of 68.1. So that means that the column would be slightly weaker in compression with respect to the y-axis because the RY value is slightly higher than the RX value, and that's what that means. And that would be it for this problem. Before I move on to the next one, are there any questions? Are we all good? Okay, I'll just go on. Now, here, of course, we have a very typical situation whenever we're pouring a concrete slab over steel girders. we like to take advantage of the fact that the concrete slab can contribute to the properties of the steel girder. And of course, we put in these shear studs, or these these are called shear connectors, and these particular shear connectors are called Nelson studs. And therefore, we want to take advantage of this and being able to reduce the amount of steel that we would need, because we're going to take the concrete here and make it work compositely with the steel. Now, here we have the modularity of the concrete, the modularity of the steel. That's always going to be 200 MPa. Okay, and basically, you always transform the concrete to steel in this case. Okay, now this is the beam size. Let me just put this on mute. Sorry, I forgot to put my phone on mute. So this is the beam size, and if this is a standard beam size that you can find, like that are produced by the steel mills. And this size, if you go into a steel handbook, you'll find that the cross-sectional area of that particular steel beam has a cross-sectional area of 8,370 square meters. It has a moment of inertia with respect to the x-axis. In other words, with respect to this, they call the x-axis, and the actual depth of the thing is 510 millimeters. I don't know why I have 310 there. That's wrong. I apologize for that. Okay, so there. So if we now transforming the cross-section area to steel, of course, we can take the modularity of the concrete in the numerator and the modularity of the steel in the denominator to get the ratio, the modular ratio, and therefore we end up with a value of, is this, hold on a second, 2500 divided by 1. This is wrong. This should be 0.125, guys. Am I correct? Oh no, because I put the wrong number here. Sorry, this is a typo. I apologize for that. This is supposed to be 20,000. That's a typo. I apologize for that, and therefore it is 10.
Sorry, sir.
Yes.
Is the depth equal to 525 millimeters? Because
yeah, it
assignment,
is. It is. This is wrong. This is also like I probably forgot to change that on my sketch, but the D here is 525. Okay, because in other words, this is a nominal depth here of 530 millimeters, but then when you go look in the steel handbook and you want to find out what the actual depth is, it would be very close to 530. It is actually 525. Okay, so it's not 320. Okay, and that was a typo because this is 200, and I did a typo here.
Yeah, I wasn't noticed, so I used 310.
Yeah. I apologize. I apologize for that. Like I said, that's a mistake.
Okay. I might get the wrong volume, so.
No, I'm just saying, but like let's say this is my mistake. I should have realized that. I should have corrected that. But that's why I put here D is 525. Okay. I hope that's the okay. So therefore, you multiply the cross-sectional area parallel to the neutral axis. Okay, and I apologize for that mistake.
Sir?
Yes.
Sir, in the assignment you wrote W310 by 39.
Oh, I did?
Yes.
It was W31 times the.
Oh, so what I did is I put a W310 by 39.
Yeah, that's why. So in the assignment 6.
Okay, let me just see what I did here then. Okay, so I put the wrong information, but I think I solved it with a W310 by 39 then. I understand what I did. The mistake was here, okay? I apologize. I should have checked this before. I thought that, okay. So what you're saying is that, okay. So what did I give you as a cross-sectional area in the assignment? Because I can go look for it. But what was the value of A that I gave you in the assignment?
4,940 millimeters squared.
So that makes sense. 4,900 and what?
40.
40. So that makes sense. And therefore the IX should be much smaller. What was the IX I gave you?
85.1.
So that makes sense. So
Times
I gave you the right values. I did the wrong thing here. So I don't. And then the D value, what was, it must have been, it's close to, what was the actual D
It's
value?
310, sir.
310?
310. Yes,
Okay,
sir.
so that's good. Okay, so I apologize for this. This is wrong. So that means that, okay. So I use the right values here. I apologize for that. Like on the, I should have just double checked. So here, the equivalent width of the concrete, you multiply the 1,000 by 0.1, that comes down to 100, and determine the neutral axis. And of course, you pick a common, okay? So as far as the values go, so it was, I made a mistake when I put the problem down. So here we go. So this was the area I gave you, and that's the area I used. The IY, of course, is, excuse me, the IY is from the centroid here, and I take it with regards to the bottom here, 155, and multiply these two together. This is, of course, the cross-sectional area of that section there is 15,000. Going from here down to there would be 385. And therefore, this gives you the IY, and then, of course, the sum of these two together. And so you get 328 from the bottom, okay? So you would be slightly into the concrete, okay? So that's what it means. Okay, so now determine the moment of inertia I of the transform section. Did everybody get the same value for the neutral axis of 328? Can we confirm that that's good?
Sir.
That's good, right?
Yeah.
Okay, so that's good. So I just screwed up on copying the problem. I shouldn't have copied and pasted. I apologize for that. So therefore, if that's good, then of course, now, guys, when you're doing this, what I like to do when I do my AD squared, okay, I take this value here, okay, and I go to this table here, for example, and I don't care which one I subtract. In other words, I don't care if I put 155 minus 328. It doesn't matter if it gives you a negative number because you're going to be squaring it. It's going to end up being a positive value. So the AD squared, right? The D is simply the D that you found, and you go to this table here, and that's going to give you the difference between the centroid of the section to the overall transform section. So that's what I tend to do. I go 328 minus 125, I square it. 385 minus 328, I square it. That's what gives me my D squared. I don't know if you guys realize that, but that's what I do. And therefore, okay. And like I said, the distance perpendicular from the centroid, I simply take this value here and I subtract that from that. I subtract that from that. And since I'm squaring it, I really don't care. And that's the first thing I do in my calculator. I calculate this term here, and then I go and calculate that term there. So, and of course here, now I've given to you directly here, okay? So I put in directly because but if you want to know how I do this, I take the two values and I do it. And then here I get 112. And of course I get an I now of 310 times 10 to the 6. Is that an answer? Does anybody else agree with that answer?
Yes, sir.
Yeah, I got the same answer.
Okay, so that's good. That means we're all on the same page. So therefore that is the right answer. And what I want you to appreciate, okay, okay. So what I want you to appreciate is that this was the initial moment of inertia of the steel, right? And because you happen to make the concrete work compositely with the steel, you're able to bring that value from there all the way up to there, which gives you a much stiffer beam, and therefore you can, of course, be able to it would be able to deflect less, it would be able to carry more loads, and so on and so on. So this is where you see the appreciation of having the concrete work compositely with the steel, so that if it was just the steel alone, this is the value you'd be working with, and now you were able to bring it up all the way to 310. So there's a good benefit of doing that. And of course, there's some additional work because you have to put in these Nelson studs and so on, and additional calculations, but there is some savings at the end of the day. So now the section, now here, I call it SB. The reason why I call it SB is because SB is the section modulus with respect to the bottom. Since the centroid is not exactly in the middle of the section, you're going to have an SB. You have a section modulus for the bottom. And I tend to call this ST a section modulus for the top, okay? And of course, as I want to know the one for the steel, I would only calculate the SB, okay? And that's why I put a subscript B, okay? So here, it's only when the neutral axis it has a line of symmetry that you only have one section modulus, but in this case, this one would have two of them. So now, the maximum stress, of course, is your bending moment divided by your section modulus, and therefore you end up getting 338.6 MPa. And when you look at this value, if you consider what steel is good for, this is a little bit on the high side, okay? But there's the stresses that, in other words, right at this point here, the stresses of the steel would be equal to 338.6 megapascal, right there. And then, of course, as you go away, all the way to zero in your neutral axis. So when you look at those diagrams, okay, and they show you these, like, for example, they're showing you the stress diagram here. So this is your neutral axis, and you want to know what the stress is at that point. Well, that value would be right at that point, would corresponds right at that outer fiber of that steel section. And I think that's it, right? So okay, so basically, does anybody have any questions before I close the assignment? Or are we all good? It's all good? Okay. Now, oops. Okay, now, do you guys, I want to know, do you guys have your ADA on? Can you show me a thumbs up next to your name, please? Okay, Yavor, thank you. Yes, yes. Olivier, you don't have your ADA on? Yes. Mateus, you have it on or not? Liam? Does that mean not all of you have your ADA on? Because if you don't have your ADA on, it's almost like AutoCAD. I'm going to show you where the thing is in the menu, and if you don't practice it, okay, so Ariana's got it on, Emmanuel's got it on, Kenneth has it on, okay, Mateus has it on, Yavor told me to have it on, Jimmy had it on. Olivier, do you have it on? Because I can wait until you guys have it on, because it's like,
Yeah, I do.
okay, you all have it on. Okay, great. Because like I said, if you don't have it on, and guys, if at any time, like I know not all of you were in my design in the AutoCAD and the drawings 2 class, but if at any time I happen to go too fast, stop and make me go back, okay? And if you don't see where I'm pointing to on the ribbons and all that, stop me. And I don't mind going back because maybe other people in your class are having the same issue and nobody just wants to say anything. So please, you know, don't because these are going to be the basic instructions on how to use the program, and these you're going to be using it throughout whatever you want to analyze with the program. In other words, so these are always going to be the same. Okay, share. Okay, so right now what I'm going to be doing, okay, oops, sorry. What did I do? What did I do? Sorry, I accidentally closed my ADA. I'm having one of those days. I'm having a bad hair day today, so. Yeah, so what I was going to do is I'm going to split. I don't know what happened. Okay. Okay, so this is ADA, and I'm going to, I don't know if I'm going to put this, I'm going to put this up next to it, okay? So what we're going to do is we're going to take this example here, okay? And I think this is an example either we did in class or something. And we're going to take this example here. We're going to model this example here with ADA, okay? And we're going to look at, for example, determine the deflection at the midspan of the steel beam, okay? The uniformly distributed load does not include the self-weight of the beam. The beam still has to be added. So in other words, remember we were able to do this by superposition. You know, you'd find the deflection of the, find the deflection of the, excuse me, of the distributed load, find the deflection caused by the concentrated load, add them up. Well, with ADA, of course, you just have to model it, and ADA will give you the deflection. So that's what we're going to be doing as an example, and then we're going to be doing more examples and so on. Now, with ADA, okay, first things first, okay, with ADA, if you have already a file stored on your computer, of course, you can open your file. Okay, so in other words, this is to open the file. And if you have nothing stored on your computer, okay, this is how you start a file right there. Okay, so I want everybody to click on that and open a new file. Okay. Now, when you open your file, this is what pops up. Okay. Now, this, what you're looking at right now, okay, is very, very similar to AutoCAD. Okay. In other words, the way ADA works is that it has values along the x-axis. In other words, just like AutoCAD, because you'll be able to put in dimensions, it has values along the y-axis. And although you don't see it here, you also have, if you're doing a three-dimensional analysis, you also have a z-axis, okay? And very, very similar to AutoCAD, when you're going from left to right, this is positive. When you're going from down to up, this is positive, and so on, okay? So this is what you have to keep in mind. What you're looking at is basically a, a Cartesian graph, okay? And of course, the same thing for the z. This is positive, and that's negative. So that's what you're looking at in terms of ADA. Now, clear all drawing, okay? So let me just, okay. Now, the first thing you should do, okay, is with ADA, okay, works both in metric and imperial, okay? Now, in this example here, we're working in imperial, okay? So therefore, I think, I know that ADA, when you start a file, by default, ADA starts in metric. So instead of you having to convert everything into imperial, you simply go to, see where I'm pointing at, where it says file? Okay, and this is, you pull down the file menu. Now, guys, I can't see you. I'm just assuming that you're following, so okay. And you go to project configuration. And you click on project configuration, and these are the dialog boxes that come up, okay? Now here, if you want, you can give it a project name. In other words, when you're creating this file for your project and so on, but we're not gonna do that, okay? So this is just so that you can keep track of, you know, like if you like, it's a nice, and when you're printing it, that this will come out with all your results, so you know exactly, and you'll just clip it or, you know, staple it to all the other results that come out of ADA. Now, under preferences, okay? Now, under preferences, this is where, for example, you can change from metric to imperial. So in our case, everything's imperial. So we can put, we change the radio button from metric to imperial. And for this here is for the, instead of having a W310 by whatever it is, I think it's a 36 or something, you don't have to worry about it. If you don't change this, every time you're going to go look at the section properties that are in ADA, they're all going to be metric, so you also have to be in imperial. So your sections are in imperial values, and your dimensions and all your resultants are going to be in imperial values, okay? So here is where you change the file from an Imperial. And guys, you can go and switch back anytime you want. In other words, you can work in Imperial, and if for some reason you want to go back to metric, you come back, switch it back to metric. You can switch. It doesn't mean like once you do it in Imperial, everything has to be done in Imperial. You can just switch back and forth as much as you want. Okay. Now, these here, I strongly recommend that you uncheck these boxes. Okay. These boxes, what happens is that as you're making the model of your structure, once you put something in, you're going to have these dialogue boxes popping up in your face. And if you don't want to have that, I strongly suggest that you uncheck these boxes. Okay. So that's number one. Does everybody okay, let me put it the other way. Who doesn't have this on their screen right now? That means we're all there. Okay. So the first thing I do whenever I open up ADA and I open up a new file, I come here. And even if I'm working in metric, I come here and I uncheck these boxes because I hate having those things pop up in my face when I'm doing my modeling. Now, this is the analysis, okay? Now, the analysis that you're going to be doing a linear analysis and all that. What's important here, this is the National Building Code. Now, here is, for example, how you can have ADA give you the results, okay? So what ADA is going to do is that once you do your analysis, and I'm going to show you, I'll make you understand this, okay? Sorry, where's the, okay. I want you to understand this. So what ADA does is, for example, if I happen to have a beam here like this, okay, like what we have here, right? What ADA does is that where you see the 10 here, okay, the number of subdivisions on the diagram. So when you put in your loads, it's going to give it, it's going to put the value at every 1/10 of the length of the member, okay? When you're going to be looking at your analysis, it's going to be doing it at 1/10. So in other words, when you look at the results that you're going to be getting and so on, it's going to give it at every, like it's going to take this dimension here, break it down into 10 segments, and the program's going to give you values at each one of these segments. Now, if you want to have more than 10, in other words, you want to see more detail, you can ask for 20, you can ask for 50, you can go up to 100. But I find that's really redundant, especially you're going to create a lot of data that in essence will not add up too much at the end of the day. But if for whatever reason you need to find a value somewhere in your beam that happens to be between there and there, well, you just come back here, change that to a 20, change that to a 30 until you hit that spot, and then ADA is going to give you the value right there. Okay, so that's what this is. Okay, it tells you each member. So for example, if this is 2 feet, okay, if this is 2 feet, it will split this into 10 equal segments of 2 feet. And if this is 20 feet, it will split into 10 equal segments of 20 feet. So you can appreciate that these values are going to be much closer to each other than these. Okay, so it's a division of the length of the member. Okay, that's what you have to keep in mind. And if ever you want to have more information, well, you come back here and you change this. Okay, like I said, values at every 1/10 of the member length, and 99% of the time it is ample for what we need to do in terms of getting the results from ADA. So that's what this is. Okay. I just wanted to. Okay. So. Okay. So now. So the ADA works in imperial metric. You can switch between units at any time when you're creating the file. So I'm going to be sending you this PDF, so it'll help you remember what we're doing. You go to the File tab, Project Management, Preferences, select the Imperial, and then remove the dialog box checks it. And we've done that already, okay? So we did that here, okay? And like I said, this is, I didn't explain that, but I want you to understand what this represents. Okay, now the thing is that with ADA, the way it works, and now everybody press OK, close this, okay? Now, with ADA, the way that this works is that ADA is you place nodes, okay? In other words, you place points where you want to model your structure. So right now, okay, right now, I will place what we call a node, right? I will need to create a node here, and I'll be able to create a node here, so that once I create those two nodes here, Okay, once I create those two nodes here, I will be able to add a member in between those two nodes. So basically, I create a node at this point here, I create a node at that point there. Now, ideally, what you should do is that to place the nodes, you use the coordinates of the node. So for example, if you consider this to be the x-axis here, okay, and you consider this to be the y-axis, and that's what you see here, y and x, okay? So what I normally like to do is I like to put the very first one right at 0, 0. That's where I like to put the first node, right at 0, 0. And then I go over, and that, in other words, the coordinates of that first node would be 0, 0. And then I'm moving along the x-axis by 16 feet, so it would be 16 feet. And of course, the y coordinate would be 0, okay? And that's how I place the second node. Okay, so that's what you're going to be doing. So what you have to do now, okay, now, so right now, clear all the drawing. Okay, now, so what you're going to be doing, excuse me, okay, right now, I want you to look at along this ribbon here, okay, along this ribbon here, and this is activate the structure mode. So when you're modeling a structure, this is the one that you have to activate. And by default, that's the first one. And you'll notice all the other ones are grayed out. That's because you haven't done anything in terms of modeling. So therefore, you won't be able to do anything else unless you model your structure. In this case, model this beam. So this has to be there. And if ever you want to go back and you want to work on your model, and for example, you have to make sure that this has been activated, okay? That's number one. So this is something that you have to keep in mind. So this is to activate the structure mode, number one. Number two, on the side here, okay, this is, for example, right now, this has been activated. So in other words, this means that I could only go and select nodes on my screen, okay? And therefore, you see that this represents for activate members, but since I haven't created a member, I can't, it's grayed out, and everything else is grayed out, okay? So now, right now, this is for the nodes. Now, if you want, you can come here, click here, and then you can try to place it, graphically, but I don't like to do that because it takes time and it's never very precise. So the first thing you have to do, okay, now, so what you do is you go under structures here. I'll let everybody take their time to find structures on the top ribbon. Okay, so click on structures, pull down the menu. Okay, so the first thing we do with ADA is that we establish where we're going to be placing our nodes. Okay, number one, and then click on nodes. And this is basically, believe it or not, an Excel spreadsheet. That's all this is, okay? Now, how many nodes do I have? Well, if you remember, I need to put a node there and a node there. So therefore, I'm gonna have two nodes. So therefore, I'm gonna put two rows on my spreadsheet. Okay, that's number one. Number two. Now, the program is gonna call the first node number one, and call the second node number two. Of course, it does it, it's sequentially, which makes sense. Now, like I said, I like to start my first node at 0, 0. Okay. By default, it gives you 0, 0 as the first coordinate. Perfect. And then the second node here is going to be at 16 feet away. Okay, 16 feet away. And therefore, what I need to do, okay, is for this one here, the x coordinate is 16. I will put 16. Okay. And that's my second node. Fair enough? So now, these nodes are not only normal nodes, but they are also support nodes. In other words, this is a pin and this is a roller. Okay, so therefore you should change the nodes into support nodes. And how you do that is you fly this out and go from normal to support. So any node that you create that is also support, you should change it to support. And this one here, the same thing, support. Okay, so now I've changed my nodes to support, and instead of just seeing a little plus sign, I will see a support graphics on the screen. Can I say okay and go on? Is everybody okay with this? Do you want me to go back and do something? Tell me, now's the time.
It's good.
We're good. So we press OK. Now, I'm going to zoom out, okay? And you guys, so in theory, here's your first support, here's your second support, okay? Now, what I like to do with ADA is that I like ADA to give me some information as I like ADA to give me some information as I'm doing my model, okay? I like to know, for example, the length of my model, of my member, and so on and so on, okay? So how do you get that information, okay, is you go here. Now, there's a keyboard shortcut. You just type in the letter O, and this is what pops up, the view options. So type O, you get this. This is the pop-up, you know, this is the the box that you get up, or you can do it from here. You have the same option. So you can either do it from here, okay, or you can just type in the letter O and it pops up, which is, you know, it's up to you. That's the keyboard shortcut. Now, we'll be going through these eventually, okay? So let's just take it one at a time. Well, I'll only talk about the very first tab now, okay? So the very first tab means that if I want to see the numbers of my nodes, I can click here. Okay, look, I'll apply, and it tells me this is node number 1, that's node number 2. So if I ever want to know where my nodes are, okay, this is node number 1, this is node number 2. That's number 1. So, and now, if of course I cannot, you know, here for my members, I don't have a member yet, but if I want to know the member number, I click here. If I want to know the length of the member, so I suggest you click. I always like to know the length of my member, and I always like to know what shape I designated my member. Well, the material, if you want, click that on, okay? Now, you won't see anything right now because the computer hasn't been provided with that information, but those are the things I like to see as I'm modeling. So I'm assured that I'm got the right, my nodes are rightly placed, therefore my member lengths are the same thing. The members are the right ones, because it does have a bearing, okay? It's going to have a bearing on certain results, okay? So you better make sure you have the right values. And at the same time, if you forget to assign these to the program, you will get an error message when you run the analysis. Keep that in mind. Now, the other thing I like to do, okay? The other thing I like to do, I want you to go to the third tab where it says graphics. Is everybody on that tab? And what I like to do is, I hate seeing that X and Y axes on my screen because I find it's more of a nuisance than anything else. So I uncheck the box here, global axis here, and I press apply and they're gone, okay? So there you go. So now, I want you to look at, does everybody have this on their screen right now? Or who doesn't have it? Don't be shy. Now's the time I can go back and make sure we're all on the same page. Okay, like guys, you can pan in, you can pan out, okay? Now, when you create a support in ADA, okay, the support created by ADA, and this is why I went, okay? This support is as if it was fixed. This support is as if it was fixed. So therefore, that's what you've created right now. This is fixed, and this is fixed. Whereas what I really have is I have a pin here and I have a roller here, okay? So what you have to do is you have to free up all the displacements that ADA fixes, okay? So once I have created my supports, the next thing I'm going to worry about is making sure I model my supports to represent what I'm actually want it to analyze. Because if I analyze as if it was fixed, it is completely different. The results are going to be completely different than if I analyze it as being pinned and simply supported. I hope you can appreciate that. By default, okay, whenever you create a support, this is what ADA creates. Fix, all around. And how you can see that in ADA, and I'm going to zoom in, is that this yellow line here means that it's restricting the displacement in the y direction. This yellow line here means it's displacing in the x direction. And that red dot that you see in there means that it's restricting the rotation about the z axis. Okay, so that's how you can tell from ADA if it's a fixed support. And let me just clear all the drawing here. So I'm going to zoom into just one so that you guys can see this properly, or you guys can zoom in yourselves and do the same thing. Okay, now I'm going to zoom into just one. Now, don't worry about these here. Okay, let me just talk to you about this so that you guys can see this. Okay, okay, this is for the three-dimensional model. So it's got nothing to do with you. So this is for the three-dimensional model. Okay, this here, in other words, if you're doing like a three-dimensional model, okay, this would be for behind. Okay, that's why they have this. But if you're just doing a two-dimensional model, okay, this yellow line here represents restrictions in the y direction. This yellow line here represents restrictions in the x direction, and the red dot is the one that restricts the rotation of the beam. In other words, fix means that that's the type of support that you're actually letting ADA want using as the support type for the model. Okay, now let me just clear this. Clear all the drawing. Okay, now I'm going to zoom out again and go back to where I was. Okay, so once I've put my supports, and I know that and I know that ADA has given me a fixed support, and I want to create a pin and a roller. Okay, you have a number of choices. Okay, you can go back to your structures, go to supports. Okay, and here is, for example, okay, so in other words, it's fixed. What does a pin mean? That means that you do not allow the rotation or the displacement, sorry, the displacement in the x direction. You do not allow the displacement in the y direction. So therefore, to create a pin, this has to be fixed, that has to be fixed. Now, I don't care about RZ because I'm not doing a three-dimensional thing. I'm not worried about MX, MZ. This is the one that I want to free. So I would put here free. Okay, so right now, what I'm telling the program that says, what I'm telling the program right now is this. Okay, it says, do not allow any displacements in the y direction. Do not allow any displacements. And then with respect to the rotation with the z direction, yes, allow the rotation. So that's a pin, and that's what I'm doing here. Okay, so that's a pin, and I free the rotation about the z axis because it's a three-dimensional program. Okay, so that's for this one here. And the pin, of course, it means that, I'm sorry, a roller means that, okay, I do not restrict the displacement in the x direction. I only restrict the displacement in the y direction, and therefore I will free it. Double click on that. I will free it in the x direction. I will keep it fixed in the y direction, but I will allow it to rotate in the z direction. Therefore, I will go and free the mz. And that's how the program will recognize that you've created a roller, because you're only restricting the displacement in one direction, and that's in the y direction. Okay, so y is fix for the roller. R is free if it's a for a pin. Rx is free if it's a roller, and of course the MZ, in other words, the rotation is always free because you want the thing to be able to rotate about the support. Okay, we're going to be doing this. I'm going to be doing this again, guys, but this is very important. Now, once I press OK, let me just clear this. Once I press OK, you'll notice that, okay, once I press OK, you'll notice that the red dot's gone. The red dot is gone. The yellow arrow is gone here, that means that this thing is only restricted up and down. And here the yellow is in the X direction and the Y direction. So that's how you can recognize graphically that now I've got a pin here and I've got a roller here. And if I happen to see a red dot there and a red dot there, that means I am not allowing the rotation about that support. Okay, so and you'll see, I can show you how drastic it's going to have an impact on all your results if you don't model your supports properly. Okay, now, so we put in our nodes, and then after that we made sure we convert our nodes that we wanted to be into support, and then after that we modeled our supports to be, you know, properly modeled so that we can have the right analysis with ADA. Now that we've done all that, the next step.
Sorry.
Yes.
Yeah, so I did exactly what you said, and my second point is still red. The second one.
That's because if okay, now can I remember I showed that you can do this, you can do it. Now can I show you another option? Okay, I told you that these menus are starting to bother me. Okay, so remember I told you can go to structures and you can go to supports, right? The other thing that you can do is that if you're here on this icon here, okay, then I can actually go and double click on this and it brings up that support. Okay, now this just tells me what the support is. It's a support type, and then when I click here, this is free fix. You probably forgot to free it about the MZ. You probably freed it either on the MX or the MY. Go back, look at your spreadsheet and see if you had freed it about the MX and the MY instead of the MZ.
Yeah, okay, yeah, I freed the MY, but I
That's
don't
right.
understand why
You
you free
understand?
the MZ
You
if
have
we're
to free
doing
the, yeah, exactly,
dimensional.
because exactly. And I'm glad you made that mistake because that's a classic mistake, okay? Like I said, you're freeing it about, okay, look, it's, you know, I apologize, it's a three-dimensional program, but you know, that's what it is. But you see, what's happening is that this is your Z axis, okay? And the rotation of the beam is happening with respect to the Z axis. Do you follow? And therefore you have to free MZ. If you were doing a three-dimensional analysis, then when you're in the other axis, you have to free it about the MZ, X and the MY. Okay, so that's why they have, but otherwise, if you leave those fixed, it will not change anything in your analysis. Okay, but you to make sure that you've done it properly, you have to free it on the MZ, and that's why you still have the red dot. And I'm glad you had that mistake. That's a classic mistake everybody makes. They always use the wrong axes about which they have to be free. And if you're absolutely not sure, free MX, free MZ, and free MZ. This way you won't have a problem. You understand?
Okay.
Okay, but you don't have to, you know, that just takes a little bit more time. I'm trying to also show you how to be a little bit more efficient on how to use the program. So right now we've got, so this is what we have. So let me just clear. This is what we have. Now we're ready. So we've created our supports. Now we're ready to add a member. Okay. So what I want to do is, okay, I want to see here where activate member. I want to activate member. That's number one. Okay. So this is, if I'm here, that means I could only select nodes on my screen. If I'm here, I can only select supports on my screen. If I'm here, I can only select members. So that's what these three icons are for. And then of course you have plates here and so on, but we won't get into that. Now, so I've activated my member, okay? And I want to add a member. So I press on the plus sign, add, okay? So I press on the plus sign. And what I do is I come and I click, I put my pointer right over that node. I click on it and then I drag over and I click over the other one, and I've added my member. Do you want me to go back and do that again?
I can just do it again, sir.
Yeah, okay. Hold on. Where's that undo button? Okay, now what's going to happen is that we won't have the same numbers anymore. It doesn't matter. Okay, so first of all, make sure that this is activated. Is that activated on your side menu, the side ribbon?
Yeah.
Okay, once that's activated, you press on the plus sign, and you see how the little plus with a little member sign diagonally to it, that means you're ready to add members. Okay, so once you're ready to do that, you go very close to where you want to. So you put your cursor right over that support, you click and you press your pick button, you pick it, and then you drag over, and then pick it, and it just added the member for you.
Okay, thanks.
Is that okay? Now, like I said, I only had to add one member, so I press the escape button twice. Press the escape button, and you can get out of that adding members. So press the escape button, okay, and you're okay. So this I was going to explain to you about the supports. Okay, so placing members. Okay, so you're going to have this to remind you on what to do, and I'll be sending you this. Okay, now. Right now, like I said, it's nice to see that this is 16 feet. That means that these two nodes have been properly placed, one with respect to the other. So that's going to be the length of my member. Now, what I need to do is I have to tell the program, well, what member am I going to be using? In other words, what are the section properties of this member? Okay, and what material is it going to be made out of? Okay, so I can, like I said, you can do everything from here. Okay, or what you can do is if you pick the member like that, the member is picked if it changes to purple. If you right click on the member, you get this little menu coming up, and you hit properties. And if you do that correctly, this is the dialog box that pops up. I'm going to do it again. Cancel. Okay. So basically, make sure that you pick the member. Okay. Now you can pick the member either by clicking on it, or you can make a window, whatever it is, but make sure that your member is activated here. Then you right click, go to properties, and that's the dialog box that pops up. Does everybody have this on their screen? Yes, no, maybe?
Yeah.
Yes.
Okay. Now, so that's what okay, so now here is properties. So click on that, okay? And this is the other dialog box that pops up. Okay, now you can have steel, you have concrete, you have timber. We are now working with steel. So I press the plus sign for steel, and this is what pops up. Okay, so in other words, you can see that it's got a whole bunch of data. Okay, and then in terms of steel, are we working with W shapes? Are we working with S shapes? Are we working with WFR shapes? Are we working with, what are the shapes that we're working with? Of course, we are working with W shapes. Therefore, we would press the plus sign there. And of course, we are looking for a W shape. So therefore, I would press the plus sign, open up the menu for the W shapes. This is where you see W right there. Okay. And therefore, I would click there. And these are all the W shapes that are being produced in the mills across North America. In other words, W44s, W40s, W36. And of course, these are in imperial numbers. Okay. So in other words, this is 44 inches, that's 40 inches, 36 inches, 33 inches, and so on. And of course, we have a W 12 by 14, which is a relatively light beam. So I'm going to go to press on the 12. And because it's a relatively light, it should be at the very end of the thing. And there we go. So there's my WL by 14 right there. Okay. So once I found the shape that I'm going to give to my member, I press the radio button. And now if you click here, it gives you all the section properties of that member, which is nice to know. Okay, but right now you don't need to know that. So that's okay. And then if you have the right member, you just press OK, and this tells you if it's available in Canada and US and so on. Okay. So now you've assigned the shape or the member designation to your member. The next thing you have to do is assign the material. So you go to material, okay, and you go to steel. Now, G40 is the Canadian steel. ASTM is the American steel. In this case, I'm giving you an American steel. So therefore, you're going to click on ASTM. And you're just going to pan down until you find ASTM A992, ASTM A992. And there you go. Double click on it. And now you've assigned the material. Now, if you want the program to calculate the self weight of the beam, you're going to have to tell the program include the dead load of the beam. And that's how the program will recognize the self-weight of the member. If you leave it at null, the program will not calculate the self-weight of the member. It's up to you, okay? Sometimes okay, so now what I've done is I designated the shape, I designated the material, and I told the program, well, when we're gonna do the analysis, I want you to include the self-weight. And if you do, you should always include it, and if you even wanna leave it out, I'll show you how simple it is to leave it out in your analysis. Now, once I press okay, this is what's gonna pop up. Remember here, under elements, I said I want to know the length, I want to know the material, I want to know the shape, okay? Well, here's the shape, here's the material, here's my length. So far, so good. I have modeled everything I needed to model. In other words, I got in the right supports, I've got the right member, I got the right designations for the member that I want to analyze, and so on. So once I've done that, I don't need that information anymore on the screen, so I don't want to clutter up my screen. I'll go back to my visual graphics and I'll just take that off. Say apply, okay. Now, this, I call this step one. I finished my model. So therefore my model is ready to be loaded. In other words, I have to put on my load cases. So the next thing I'm going to do is go to loads. So my structure is complete. I go to loads. Okay. And pick load cases and pick definition. So loads, load cases, definitions, okay? Now, you see automatically, because you told the program to calculate the self-weight of the member, it created a load case for the self-weight, and that's called dead in this program. So leave that the way it is. Now, you can create another load case. So let's call the other one live, okay? L-I-V-E. In other words, it's a live load that we're going to be putting on our member. It really doesn't matter. This is just for you. You understand? Like if I'm doing snow, I would put snow. If I'm doing live load, I would put live. And here, you don't have to do anything here, but if you want to define what this is for the program, this is just your name so you recognize what you're working with. If you come here, okay, and you double click on live, when it comes to combinations, you can ask the program to generate the combination for you, but it's going to generate every possible combination, and I find that that's a waste of time. So it's up to you. If you don't happen to change this to live, it won't change the difference in your analysis. It only becomes different when you want to do the load combinations, not the load cases. So right now I have two load cases. I have the self-weight.
Excuse me, sir?
Yes.
How do you get the live type?
Here?
Yeah.
Okay, so like you double click on that. Okay, hold on, I'm gonna close this. Okay, when you double click on this is what you see. Okay, you see 1995 National Building Code, the National Building Code, press on the plus sign for the 2005, 2010, 2015 National Building Code. Okay, and if you pan down, you see live here. That's your live load, and therefore you double click on it and it becomes alive.
Oh, okay. Yeah.
And if you don't do it, I don't worry about it. It's not gonna affect your analysis, okay? But I'm just showing you that if you want the program to generate the load combination, you should assign the type in, because here, this is your name. Just because you call it live here, I could have called this live 1 or whatever, okay? So this is me. This is the program, how it recognizes that it's a live load, okay? So now that I've created the load case, okay, I press okay. First of all, does everybody have two load cases on this spreadsheet?
Yes.
Mm-hmm. Okay. Now, okay, so press OK. Now, we are ready to assign loads to our member. So if you come here, you remember this used to be grayed out here before when we first opened the thing, and now it's no longer grayed out. You see that? It's no longer grayed out. That's because you have created load cases, okay? So if I click there and now, okay, structure dead load, and I click on save the project, say yes, okay, save it. Save it where you want to save it. I'm going to save it under, anyways, let's see. Let me go to, save it wherever you want to save it. Okay, here. Example number 1, okay? And I'm going to save it here on inside my Dawson file, and I'm going to save it here. Doesn't matter. I'm going to be deleting it anyways. So I saved it. Okay. So now all the work I've done so far has been saved, which is great. Okay. So now, first of all, has everybody activated a load case? That's very important. If you haven't activated that, you won't be able to do anything. Okay. And then once you've activated, you fly out the menu and you go pick which load case you want to now work with. And of course, the dead load, I don't have to worry about it. That's already built into the program. The live load. Okay.
Can you have multiple ones at the same time?
Sorry?
Multiple case loads at the same time? Or
But
it's one by one?
why would you want to do that?
Well, let's say you've got two forces. Let's say you've got 10 kips there and 20 kips like at
Okay, so
Yeah,
those are
22.
different values, but they're all live loads.
okay.
You understand what I'm saying? Like the 10 kips is a live load, the
okay,
3
so
kips
it's
per
just
foot is a
the
live
okay,
load.
so
In
it's
other words, the
just
value,
the type.
pardon?
It's just the type.
Well, I'm just saying,
You just say like you're adding live load.
in other words, right now, like I'm adding all the live loads onto my beam. You understand? Now, if this 10 kip was a dead load, right? Then I would create another load case and I would call the superimposed dead load and I would put that under dead load. You see? So what you do is that the load cases represent the type of loads that you're putting onto your structure. That's what it is. Okay. So right now I got live loads. So now, excuse me. Okay. So now I see my member's already been highlighted, but okay, so I'm going to highlight my member. Okay, I'm going to right click. I'm going to go to properties. And this is the, okay, now this is the, dialog box that pops up for the load. You notice here it says live load, okay, and it says PLF. That stands for pounds per linear foot. And I got kips per linear foot. Okay, so I can, of course, take this and multiply it by 1,000 and put the right value here, or I can simply right click here and I can say change units. Okay, and I go down to kips per linear foot. So this way I don't have to do any math in my head. Okay. Okay, and now it's all in kips per linear foot. Okay, now I'll do that again. Right click on loads where it says, you know, change units. Okay, and then you can fly out this menu and you can pick what this is: pounds per linear foot, kips per linear foot, kilograms per meters, kips per inch, pounds per linear inch, you know, newtons per millimeters, kilonewtons per millimeters, and that's where you change your units. Okay, now this is how many decimal places do you want to show your load. This determines when it's going to be displayed. So how many decimal places? If you want to have 3, put 3. If you don't have any, put 0. This is just the decimal places that you're going to be inputting your values. Okay.
Sure.
Yes.
Yeah. How did you get that to that tab? The loads on the member.
Like see here where it says loads right here.
Yeah. No. Well, I don't see the tab itself. Like I don't have the.
Oh, okay. What you have to do is like, first of all, is this what you're seeing right now on your screen?
Yeah.
Okay, so make sure you highlight it. Highlight the member.
Yeah.
Right click on it.
Okay.
Go to properties. Okay.
Okay.
Okay. And if you or if you wanted to, you could have done it from up here. You understand? It's up to you. You understand?
Okay.
But so in other words, properties. Now, this is distributor load. Okay, so therefore, like I said, and so give you a chance to change it. Like go right click on that on that row and go and change the units. Okay, and make sure you take kips per linear foot. And fair enough. Now, I have only one distributor load, therefore I only have to add one row to my spreadsheet. Okay. Now remember, okay, ADA works with signs. Okay, so ADA works with okay, so if the load is going down, right, ADA has to see that as a negative value. If the load is going up, as you're going up the y-axis is positive, as you're going down the y-axis is negative. So therefore, if you want ADA to put the loads acting downwards, okay, you have to put it as a negative value, okay? And that's in the Y direction. In the X direction, the same thing. If my load is going from right to left, it becomes a positive value. If it's going from left, I'm sorry, from left to right, it's a positive value, from right to left, and then I have to put a negative value. So this is how I designate in ADA in which direction you're going to be applying the load. That's number one, okay? So right now, okay, so here I'm going to be putting -3, and of course I have the right units, kips per linear foot, and here and then you'll notice that automatically it went to -3 here. Okay, now if ever you want to create a trapezoidal load, and we'll do it in one of the examples. Okay, you simply put, for example, if I were to put -3 here, and I would put 0 there, what ADA is going to do is going to draw it like this. Okay, so this is the, okay, where you started, and this is where you're ending. And in this case, you're telling ADA put the same load right across the whole member, and therefore that's how you, and we're going to do an example where we're going to be doing a trapezoidal load, so don't worry about it. So that's a distributed load. We also have a concentrated load. So therefore I change tab, okay? And again, okay, I press. Now, what I wanted to explain to you is that I hope, okay, that you remember how you assign the member. If you clicked it here and then you went and clicked there, this is what is called the I node, and this here is called the J node. Okay, the I node is the starting node, the J node is the ending node. So therefore, if you click here to here, the distance would have to start from this side. If you happen to do the other way, then you have to reverse everything in terms of giving the information. So keep that in mind. I always start from left to right. So therefore I know I, J. So I know that when I have to give the information, I'm always giving it starting from this reference point, going to that reference point. That's very important, okay? So that's number one. Okay. And I'm going to repeat that, okay? And then the other thing is that, okay, so where is this thing placed with respect to the IJ? So if I see here, it's at 6 feet. So therefore, I'm going to put 6 feet here, okay? Now, what's the force? It's going downwards, and it's -10 kips. So the units are good, so I'm going to be putting -10, okay? And there you go. So now I've put in my concentrated load, and I positioned it at 6 feet away from where I started my member. In other words, 6 feet away here. And I give it a value of -10 kips. So if I press OK, okay, now it looks kind of bizarre, but if I click here, it's going to bring everything back to normal. Okay, so now I have a concentrated load of 10 kips, right, acting right at that point here, and I have a distributed load of -3 kips. And if you want to see your units, it's all up here. Now, if for whatever reason you want to see the numbers a little bit bigger, you just press here. You get the bigger numbers. If you want to see the loads getting a little bit bigger, you can press here. This is how you can play with the graphics, okay? And you can also tweak how these things actually show up. It's up to you. And if you want to bring everything back to normal, you just click on that little thing. So this just brings everything back to normal. And so there you go. Now I've loaded my member with the loads that I have. Fair enough. Perfect. And I'm ready now to tell the computer how to combine these loads in my analysis. Okay, so therefore, first of all, does everybody have this on their screen? Or does somebody not have it? And if they want me to go back, I'll go back and do it.
Just a question. How do I make my arrows smaller?
The arrow smaller?
Yeah.
You'd have
Yeah,
to
like
go.
my 10 is massive.
You have to go here, and you have to go play here. And I don't want to waste that time right now. Okay, so I'll show you that, but this is where you can go adjust all your visual graphics. Okay.
Okay, yeah.
Okay, so I don't want to get into that right now. It's only going to take a lot of time for nothing, and fair enough. So that you can adjust all your visual graphics with this. You just here, for example, structure, and you want to adjust your loads, right? Is that what you want to do? Loading, okay. And you want to adjust your arrows. So you click there and you start playing with the ratio, and you can adjust everything. Okay, so by all means, I'm showing you where you have to go. Tweak, play with it, have fun, enjoy, you understand? So, Okay, so I just wanted to show you, the only option that you have here is to either make it, you can make the text bigger or smaller, you understand? Or bigger, or you understand? Whatever. And then of course, so these are the options you have right here on the ribbon. All the other things you have to go and adjust them in this visual graphics dialog box. Okay, if we all have that, don't worry about the arrow size, that's just graphics. It won't affect your analysis or anything. Now, I want to tell the program how to, so we've done that. Okay, now determine the load combination. So I'm going to go to loads. Everybody should click on the pull down menu load, go down to load combination. Don't go to generate. This is where I say the program will generate all the load combination for you. Go to definition. Okay. Now, right now, you don't have any, you're going to create one. So you press on the plus sign. Okay. And and for example, you can give this a name. Okay. For example, if you were doing like, you can call it strength, or you understand, whatever you want to call it. Or for strength, I don't want to get into this, but strength, or you can call it live. Okay. Live plus self weight. You understand? You can call it whatever you want. You understand? Plus self weight. This is just for you to remember what it is. And then after you created one there, you go to load factors. Okay. So this is the one that you're going to be in. And this is where you tell the program how to bring each load case into this load combination. So you would press on the plus sign here. You would press on the plus sign here. You create at least two rows on this spreadsheet. And then you double click here. You always want the self weight of the member. That's load case number 1. And then of course you want to have the live load. Now you leave the load factor equal to 1.0 because you're not doing any design here. You want to see the results as if it was a specified load. So leave that as 1. And next year when you guys are going to be doing limit state design, you'll learn how to modify that to the value, the proper values depending on the type of loads. But for this year, leave it at 1.0. So if you did this correctly, like I said, create one load combination. You call it, I should have renamed this, but okay. Once you create one there, you change the tab, and this is where you tell the program which load case are going to be going into that load combination. And if you press OK, now you've got your load combinations. You're ready to do your analysis. Now I'm going to have to move this over a bit because I don't see it. Now, to run the analysis, you can, of course, you can go here to analysis and say static analysis. You see the FX, that's static analysis. You either do it here, or if you want to do it from the ribbon, you can do it here. Okay, so it's up to you. You're doing exactly the same thing. It's just 2 options with ADA. So if I do FX here, save project, yes. And I say analyze, and look at that. Calculation is complete. You may review your results. So it's already done. So it's done all the calculations. Okay. Now, this is what I want to look at. The load combination that I created. Now, you don't see anything here. That's because you haven't told the program what you want to see. So normally when I'm doing this and I'm doing the, okay, so type in the letter O. I'm sorry, not 0, O. No, sorry. Okay, type in the letter O. Okay, now if I go hit the result tab, I want everybody to hit the result tab on view options. Okay, the first thing I like to look at, okay, when I ever do the analysis, I always like to look at my reaction. So I want to see RY. Okay, and if I click here, it's going to show me the direction. It's also going to give me the numerical value. So I press apply. Okay, and of course, this is way out of whack, so I'm gonna just do this. So right now, this is the RY value on the left. This is the RY value on the right. And of course, I don't have any RX value. It's 0, and of course, I have no moments. So those are my reactions. Okay, so that's reactions. And then if you want to see what are your units, you look up here. This is in kips. So if you got 30.36 and 27.7, that's why sometimes I like to run my analysis without the self weight, okay? and check it to see if the sum of f of y's add up to 0, and therefore I know that the analysis is pretty good. I haven't forgotten anything. Otherwise, it only makes it a little bit more complicated to add the self-weight. So those are the reactions. Now, if I go back here, I see my reactions, and you shouldn't clutter your screen. You've seen your reactions, and you should actually, you know, either print this page and save it, or write them down on a separate piece of paper. Now, Vy, okay, are your shear forces, Vy. Okay, Vy are your shear forces. In other words, they're shearing about the y-axis, and I press apply. There's my shear diagram. And if you remember what I told you, that you asked for analysis of 1 and 10, what it did is it took this length here, broke it into 10 segments, and it's giving you values at every 1/10 along the member, okay? Now, this is just graphics, okay? But don't forget. So there's your shear value at both ends. And of course, this is supposed to correspond to your reactions, because they're very much the same, the reactions, okay? So those are your shears. And of course, now that I see my shear, I don't want to see my shear and my moments at the same time. Mx is the moments about the x-axis, and therefore I want to see the value. Apply. And there's a bending moment. Okay, so this is the bending moment. Now, ADA puts the bending moment, okay, sorry, in the direction, sorry. Okay, there's your bending moment. And do you guys have your bending moment downwards or upwards?
Downwards.
Okay, that's because I've corrected it on ADA. ADA, I shouldn't have corrected it because I've already been using this program, okay? ADA will give you the bending moment in the direction of the deflection, which is like, but you guys are used to seeing that positive moment is above and negative moments are below. So if you want to change that, that's one thing I'm going to show you how to do today. You go to view options, okay? Go to colors, go to results, go to, sorry, go to members, go to bending moment, go to strong axes, double click, and change this to a positive value. In other words, right now on your screen, you should be seeing a negative value. If you change that to a positive value, leave this. If you change this, it's just going to change the amplification of the graphics. Just change this to a positive value, and you're going to see it going upwards, the way you've normally been seeing it in all your physics class and so on, okay? Now, so that's, you're seeing things graphically. And of course, last but not least, if I go and I look at my results, I've seen my moment. Now I want to see my deflection. And of course, I want to see the deflection with respect to the strong axes, okay? Press apply, and there's my deflection, 2.3 inches. So now, if ever I want to see all these results in table form, right? I simply double click on the member, and there it is all so this here is your highest bending moment is right there, and it's happening right there. This is all your shear forces, okay? And of course, this is all your deflections. And everything else is 0 because you don't have any tensile, you don't have any axial force, everything is 0. And of course, you're not doing anything in 3 dimensions, so these are all 0. So this is your bending moment, this is your shear, and this is your deflection. And if you want to see it, I like to see my values, I like to see them graphically, if it makes sense, but I like to work in table form because I like to take these values, copy them, and paste them in my Excel spreadsheet and work with them on my Excel spreadsheet. And clear all drawing. And of course, once you've done that, you close. And I've seen people do this, and I find that this is really, really not practical to do this. They put their deflections, they put their bending moment, they put their shear, they put their reactions all at the same time. Okay, they put their reactions and they say apply, and they don't even know what they're looking at. That to me is like really bad. Okay, so if you're going to do that, you might as well just double click on the member, go look at it on your spreadsheet, okay? close. So, okay, so that's basically what ADA can do for you. So instead of you doing this all manually, once you've modeled it properly, once you've loaded it properly, and you did the right load combination, you run the analysis, you get everything that you want from your analysis. You get the moments, you get the reactions, you get the shear, you get the deflections. So is everybody okay with this so far? Guys, are you good?
Yeah.
Okay. Now what we're going to do is we're going to model this one. Fair enough. We're going to model this one and, excuse me. And this is, I think we did this one in class, and I want to show you, like, you know, like, of course, we did this by superposition, where we removed this, calculated deflection, we calculated what the force would be to bring that deflection back up to 0, blah, 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 calculate the reaction here, and then we were able to calculate the reactions there. Well, I'll show you, excuse me. So basically now you want to start a new file. So therefore, you want to start a new file. So you click here, new, okay? And you're back to this again. Is everybody there right now?
Yes, sir.
Okay. Now, okay. Now we are going to start, okay? Now, like I said, when you start a new file, always go to your preferences, okay? So in other words, go to File tab, pull down the file, go to Project, go to your, sorry. Excuse me. Okay. And then you go project configuration, okay? And then you go to your preferences. Like I said, here, this is all in metric. Great, we are working in metric, so make sure that you're in metric and in metric. So change that back to metric, okay? We're gonna be working in metric, and at the same time, remove these dialog boxes, okay? So that they don't pop up in your face as you're doing your model. And like I said, this is where you change, if you want to have more values along each member, this is where you would break this, change this to 20, 30, 40, 50, okay? Like I said, I don't do that. I leave it at 10. It's ample for what I need to do. And once I've done this, I'm ready to go. Fair enough? Now, like I said, even before I start modeling, I like to tell the program, okay? I like to know where the lengths of my members are going to be. I like to know what the shape of my member is and what are the materials that I've assigned. I like to see that right away, okay? And after that, I don't like to see that those big coordinate axes in my face, and I like to remove that from my screen. So I go to the third graphics, to the second box, I uncheck it, and I press OK. So of course, now I got a nice blank screen, okay? Now, before you run to ADA and you start worrying about, okay, what you should do is always remember, you have to establish where am I going to be placing my nodes. I need a node there, I need a node there, and I need a node there. So that's number one. Number two, what I'm going to be doing in the back of my head is I need to know, well, what's the coordinate of the first node? Well, this is going to be 0, 0. What's the coordinate of the second node? Well, this is going to be 5. If I'm working in meters, 5, 0. And what's the coordinate of the third node? This is going to be 8, 0. Because I'm not moving anywhere along the y-axis. That's why it's always a 0. Okay. So that's the first thing I need to do. Okay. So I do that on my sheet of paper, and then I run to ADA and I start putting in my nodes. So just like we did before, you go to the structures tab. Now here, of course, you see everything's grayed out here, right? Like I told you before, you can't do any loads because you haven't even done anything on your structure. This is automatically activated when you turn on the file, so you don't have to worry about it. But if ever you're doing something and you've already created your model, you put in your loads, you need to go back and modify something on your model, remember you have to activate the model here, otherwise you won't be able to do anything on your structure. So this is very important. Now, the second thing is that I'm on nodes here. I can, like I said, so I go to structures, I go to nodes, And now I have 1, 2, 3. So I have 1, 2, 3. I like to click right away. All of them are support nodes. So right away, I'm going to change this to a support node, change this to a support node, change that to a support node. So I won't forget. Now, the first one starts at XX. Now, I'm working in meters here. If I want to work in millimeters, I can change that to millimeters, but why put in all those extra zeros? The second one is at 5 meters. And the third one is at 8 meters. Okay. So there, now I've given it, okay. And therefore, if I press OK, that's what pops up on my screen. So there are my 3 supports, okay, that I've just created for my model. Now, like I said, by default, this would have been fixed, 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 and therefore now I got to go create a pin here, a roller there, and a roller there. So therefore, what I'm going to do is I'm going to, okay, I can do it either through here, through structures, okay, supports, and so the first one is here, fix, fix, X and Y is fixed, but MZ is free. The second one, MX is free. MZ is fixed because it doesn't move up and down, and MZ is free. And the third one, MX is free. In other words, it's free to go back and forth in the X direction. It's fixed up and down, Y direction, and it's free to rotate about MZ. So that's what you should be doing in order to create. The first support is fix, fix, free, means it's a pin. Free, fix, free means that it's free to move along the X-axis, not free to move along the Y-axis, but free to rotate about the Z-axis, so that becomes a roller. And here in this case, I have 2 rollers, and therefore I will create 2 rollers. And as I said before, if all of a sudden you don't see a red dot there anymore, you don't see a red dot there anymore, you don't see a red dot there anymore, and you don't see a yellow line here or a yellow line here, then this has become a roller, this has become a roller, and this has become a pin. Once I've modeled my supports correctly, of course, I will always activate the member. Okay, and now I'm ready to add members. So here we go. I've added my first member. And remember, if you notice, I started from this node to that node. That means everything that I do later on, this is my I node, that is my J node. So when I need to position something on this member, the computer will start from here and make its calculation starting from that point. And click on that and click on that. So far, so good, okay? Now, so I've added my 2 members. So now I can escape to get out of the command. Press escape, I get out of the command. Hit the escape button on your keyboard. Now, since both of these members have exactly the same properties, okay, so I can pick them both at the same time. So I do a window around both of them, and I pick them both at the same time. Or if I didn't want to do that, I could have picked one, hold the control button down, you have to hold the control button down if you're going to be picking individually, if you want to keep adding members, okay? So it's either you do a window, just like in AutoCAD, escape, or if you hit a member, if I pick the other one and I don't hold the control button, it's just going to pick the member by itself. If I want to pick both, hold the control button down and I pick both of them. It's up to you how you want to pick your members. And since they both have the same properties, I'm going to do them all at the same time. Once I've picked all my members that have the same properties, I right click on the member, go to properties, okay? And just like before, okay, I come here, this is where I add my properties, okay? And in this case here, I have the steel properties, right? And of course I have W shapes, and I'm going to go to W shapes. And in this case, the W shape is a W200 by 19. So therefore I will go down to the 200 here, W200, and open up all the different weights or masses by 19. I have it right there. And that's the one I'm going to be assigning to both members, a W200 by 19. Press OK. And like I said, this, if you want to see the properties, press OK. Now, as far as the material goes, okay, I'm going to do steel. And here I say it's the same thing. I told you it's American steel, so I might as well go down, pick the American steel until I find the A9925. And I double click on it. Now I've assigned it 0. Now, in this case here, I will not include the self-weight of the member. Because if you guys want to compare the results of ADA with what we've done manually, I'm not going to be including the self-weight of the member. So I'm going to leave that as null, okay? So, but if I wanted to include it, okay, I'm going to put null. This way, But if you want, okay, I'll show you that if you want to put it in anyways, and then I'll show you how to, okay. If you want to exclude it when you do your load combinations, you don't even have to, whatchamacallit. So here we go. So I press OK. Now, like I said, since I've told the visual graphics that I want to see the member designation, I want to see the length, I want to see this just to reassure me that I'm doing everything I want to do. I haven't made a mistake in placing my nodes. I haven't made a mistake in assigning the right section properties, and I haven't made a mistake in assigning the right material. If I'm happy with what I see here graphically, everything looks good. So I'm simply going to take that away. I don't need that anymore. That's just for me to double check, and therefore I'll take that off so that it doesn't clutter my screen. Apply. Okay. So now, as far as I'm concerned, my model is complete. Okay. And the next thing I need to do is, of course, create load cases. Okay. So just like we did before, we go to loads. So, and we go to load cases, and we're going to define our load case. So now I've activated the dead load, doesn't matter. And I'm going to call this one again. I'm going to call this one live again. I'm just going to call this is my live load. Okay. And if you want, I'm not even going to define it, but if you want, you can define it, and you come here. Okay. And you can define it, but I'm not even going to define it to show you. I want you guys to define it. I won't define it. It won't make a difference in my analysis. I just want to make you aware of that. Press OK. Now, when I'm ready to assign the loads to my members, okay, I have to activate a load case. So I have to go from activate a structure mode, I have to go to activate load case. Very important. Once I do that, this is going to pop up. And of course, I want to activate the live load. Save the project, yes. Okay, I'm going to call this desktop Dawson X2, example 2. Okay, save. Okay, now, only in this case can I pick both members and assign the loads because they have exactly the same load on each member. So this is the only time I will actually pick both members and I'll assign both members the load. That's number one. If you should not do this unless they have exactly the same load, okay? I'm telling you right now. If one member has a slightly different load, you have to load each member individually, okay? Now, like I did before, I will right click, I will go to properties, and of course, now I got a distributed load. I am in kilonewtons per meter. I don't have to change my units. I only have one load, so that's good. It's going to go through the whole, in other words, it's going to go through the whole member. So here I'm going to put minus 15. And of course, it's going to go to minus 15. And if it starts at 0 and it goes all the way to the end of the member. In other words, it starts at 0 and it goes all. Now, if ever you happen to have, it partially loaded, then you have to put the fraction of the length here to tell how far down is that load going to be applied to the member. But here I'm going right across the whole member, and therefore it's minus 15. If I press OK, well, this is what I see. Okay, and that's exactly what I want to see. I want to see 15 kilonewtons per meter across everything. Perfect.
Sorry, sir. Could you repeat one more time?
Sure. So first of all, did you create your load case?
Yes, I did.
Once you've created your load case, did you activate your load case?
No.
Okay, so that's the first thing you have to do, activate. And Jimmy, you should have stopped me 5 minutes ago, not now. Understand? Because this is the step that you missed right here. Activate your load case.
Oh, I see. Okay, it's activated. Yep.
Then once it's activated, this is going to pull out and go and click the load case that you want to add to your member. Pick live.
I did that. Yeah.
And then pick both members in this case because they both have exactly the same load. And you right click and you go apply the load to both members. Is that good, Jimmy?
When I right click, it shows properties.
Exactly. Hit properties because you want to put the properties of your load case on it.
Oh, okay. Oh, okay. I saw it. Okay. Thank you.
Okay, now you can put -15, and then you can close it, and this is what you're going to see. Okay. So now that I've assigned the loads, okay, I got to tell the program how to combine all the loads. Okay, so I'm going to go back to loads. I'm going to go back to now load combination. I'm going to actually define my load combination. Okay. And of course, I'm going to have one load combination. Call it what you want. Okay. Call it live or call it whatever you want. That's for you to remember what it is. Okay. And then and then this is where, okay. Now, what I'm going to do here is I'm going to exclude the dead load. Even though I told the program to activate the dead load, what I'm going to, if I want to exclude the dead load, then I just put the live load in my load combination. I don't put the dead load, and the program will exclude the dead load. Okay, so that's how you do it. And if you ever want to do the analysis with the dead load, you press here, create another row, and go and get dead load, and it will include the self-weighted member. So that's how you can exclude it in your load combination. Okay. So right now I'm excluding it, or I'll show you. I'm going to do it this way, and then I'm going to show you. If I happen to put the dead load, I mean, this is redundant. If I do this and I put 0 here, what's going to happen? The program is going to multiply by 0. The dead load is going to be, so in other words, I'm just telling you that. So in my case, I'm simply going to delete this. Where is that delete? Okay, I'm only going to be putting that live because I want you guys, if ever you guys go back to wherever we did this problem, I want you to check the results that we did manually with what the computer did and see if the computer gives us the same results. You press OK. So I hope you guys are starting to appreciate that you model. That's your first major step. You do your load cases. That's your second major step. Then you do your load combinations. That's your third step. And then after that, you're ready to analyze. Okay. Right now, I'm ready to analyze. So in other words, I press FX, save the project, yes. Analyze, and it's already done. Okay. It says calculation complete. You can, so close. Okay. Now, you want to see your live loads. Okay. Now, of course, I don't see nothing because I haven't told the program what I want to see in terms of my results. And like I said, when I see my results, I always like to look at my reactions first to see if it makes sense. Okay, apply. Okay, and here I end up with 78.85, 30.43, and 10.72. And if I remember what we did in class, I think that's pretty much what we're supposed to be. So there's my reactions. Okay. Now, if I want to see this a little bit bigger, of course, I just press on this. Okay, get to see them a little bit bigger. And of course, this tells me the direction. And if ever I want to see the values, I make sure, like here, I press here on the supports. This is for the supports. I simply double click on this, and it will give me the value right there in table form. So RY is 43.43. Okay, if I want to see this one. Okay, so there's a number of ways you can look at your results. You can either look at them on the screen, and you can also come here and look at results. Okay. Okay, sorry. You know, like if you want to see your support reactions. Okay, so and so on, because I have this one picked and so on. So that you have a number of options. So those are my reactions, and of course. What I want to see is sometimes I want to see my shear forces. There I go to VY for my shear forces, apply. There are my shear forces. And if I want to amplify the shear diagram a bit, there's my shear diagram. It looks pretty good. And of course, last but not least, the moment diagram, MX, apply, and there's my moment diagram. Okay. Like I said, if you go here, and you go to colors, and you go to results, and you go to members, and you go to bending, and you go to strong axis, and if you change the amplification factor to a positive value, it will flip the whatchamacallit. As a matter of fact, if you look at the shear diagram, okay, I haven't flipped the shear diagram, but if you look at it, okay. If I come here, and if I look at the results, and if I look at my shear diagram, okay, apply, okay. Well, the shear diagram is not the way we've been seeing it. We always have, this would be up, so therefore I can do the same thing for my shear diagram. If I want to see it the way I usually to see it, in other words, this should be positive, then go down negative, then positive, and so on. I do exactly the same thing. I go to results, colors, I go to results, okay? Members, okay? Shear forces, the strong axes, okay? Put a negative value, apply, and there you go. So I just reverse the amplification factor, and that's the way we normally would see the shear diagram, okay? So guys, now, oh, and then of course, if you want to see some deflections, you simply go to the results, okay? Go to results, take off the shear, okay? Take off the bending moment. Always you want to see the strong axis deflection because that's where it's bending about, apply, and there's your deflections. But mind you, the deflections here would be very hard to calculate even by superposition. No, not really. Yeah, really hard to calculate by superposition. And that's it. And like I said, if ever you want to see everything like I like to see it, if ever you want to see everything in a spreadsheet, I'm sorry. Okay, make sure you're on member here. On the select the member, double click there, you get all the values for that member. And then you double click here, you get all the values for that member. And that's all your bending moments, your shears, your deflections, and so on. Now guys, it's 11:46. I'm going to give you two options. We can either continue until we finish a lecture, or we can come back at 2 o'clock and continue during the lab. What do you guys want to do? Because I think I have one more example to go through. No, I got 2 more to go through. So what do you guys want to do? Would somebody give me an idea?
Can we have a 10-minute break and continue our class? Well, that's my idea.
We can take a 15-minute break and continue, or no, because if we take 15 minutes, we're going to lose the Zoom meeting. You understand? We can take a 10-minute break and then continue, or we could come back at 2 o'clock and continue at 2 o'clock. What do you guys want to do? Can somebody tell me? I mean, like all I have is like Jimmy says he wants to continue.
Well, we can do it at 2 o'clock
It's up to you guys. What do you want to do?
to give us the time to eat. 'Cause
Well,
10 minutes is not
exactly.
much.
So like we all come back at 2? Does that sound okay? Sorry?
When is the assignment due? Is it still
6
due at 4?
o'clock. 6 o'clock.
Oh, 6.
Yeah. Okay. So, and plus, like when we come back, we'll probably only take about an hour, you understand? And then I'll still stay online after that. If you guys are having any issues, I can help you with your things. And then that by 6 o'clock, you should be handing in the assignment. Is that okay?
I just have a question.
Yes.
Like from 4 to 6, I have a class.
Oh, you have a
So
class. Okay.
So can you push back the assignment? Can we make it later?
Yeah, sure. I can make it for the end of the day.
Okay.
How does that sound?
Yeah, that sounds good.
Okay, so
Yeah,
I'm
'cause
gonna
I
have
have
to,
a class.
pardon?
I also have a class.
Okay, so what I'll do for today, I'll make the assignment due for the end of the day. How's that?
Perfect.
I'll just go back to Leah and change it to the end of the day. Sounds good?
Yeah, that's good. Thanks.
Everybody good with that? Okay,
Yeah.
so listen, guys, have a good lunch. I'll be back at 2, and come in at 2, and we'll continue from here. And then after that, I think by 3 o'clock we should be done. And then after that, you'll have an hour to ask me any question. I'll stay on until 4 o'clock, guys. Okay, so that I want everybody to start really, because these are the basic inputs that you're going to have to be able to handle. Because after that, it's always going to be the same thing, but the structures are only going to get a little bit more complicated. Fair enough? Okay. So see you guys at 2. Have a great lunch. And in the meantime, I'm going to go and change the Leah to end of the day. So nobody's going to have to panic. Okay. Sounds good?
Yeah.
Thank you,
Okay.
sir.
Yes.
Thank you.
Okay. Wait, it might even be too late for me to go change Leah. So if all of a sudden, I'm going to see if I can change it. If I cannot change Leah for whatever reason, guys, don't worry about Leah, submitting it through Leah. Take your PDF and then just send it to me by Mayo. Fair enough? Okay?
Okay.
Yes. Okay, so I'm going to, hold on a second. So guys, we'll see you at 2 o'clock. We'll continue at 2 and we'll escape. Where's the, stop sharing. Okay, guys, so have a good one and talk to you later, okay?